Hi everybody, welcome, and this is Jim Corkins. We are continuing on with our lecture in electric charge, but specifically we are going to be doing the Coulomb's force in one dimension. So this is an offshoot of force diagrams. Specifically, we're just going to be learning about the Coulomb's force equation and creating little mini force diagrams in one dimension. Now, before we go through that, I want to make sure that all of you go through and review the video on vector addition in one dimension. That will help you tremendously when you are doing force diagrams. Okay? Now, the Coulomb force equation. All right? The Coulomb force equation is talking about in 1.0, that last video we saw, about how charges are electrically repulsive or attractive. So as you remember, like charges repel, unlike charges attract. So when we're looking at two charges interacting with each other and they're repelling each other, they're creating a force. And specifically that force is called the Coulomb's force. Okay? And those the repulsive force that we're talking about here is, we're going to write it as k q1 q2 all over the distance apart squared. And we're going to get into that equation and we'll get into what all of that means. But k, let's start off with k. K in the front, it's written as uppercase or lowercase. It is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity constant of free space. So we're not going to worry about the 1 over 4 pi epsilon naught right now. Later on in our calculus class, if you're doing physics 131, when we get into Gauss's law, we are going to get into 1 over what the 4 pi epsilon naught really means. But for right now, we're just going to use k, and k is really efficient in the fact that it's basically just 9 times 10 to the 9th newtons meter squared per coulomb squared. And if you remember, a coulomb is a charge, okay, where both positive and negative charges, we're going to write them as q's. So a positive q, actually I'll just write that in black. So the charges for a single charge is plus or minus 1.6 times 10 to the negative 19 coulombs. And that's the charge of one single positive or negative. Okay? Now, how we are going to write our equations, it's written in your books pretty much like this, right here. But I want us to write it like this. So we're going to write our force equation, our Coulomb force equation, as, we're going to put our brackets first. We're going to write it as Q1, and then the K, Q2, all over R squared. And the reason why I want us to write it like that is this part right here. It's the electric field of the other object acting on our charge. So this is the charge. Q1 is the charge that we're doing the force diagram. So right here, this would be Q1. And see how it's got a force arrow where it's being attracted to this positive charge right here? So this force arrow would be Q1 is being acted upon by the electric field of Q2. And they're this far apart, which is a distance r apart. Okay? So we're going to call this distance a distance r apart. If it's in r is a good placeholder, it's either x, y, or z. If it was horizontal, it would be in the x direction. If it was vertical, it would be in the y direction. So we'd put x squared here or y squared there. But basically, we're writing this force this way because when we get into the electric fields equation, you're going to be so used to writing this, your brain will automatically put this together as the electric field of the other object acting on the object that you're doing the force diagram on. So a Q1 is experiencing a force due to the electric field of Q2. And that electric field is written as KQ2 over R squared. Okay? So this is the basic equation of how you write it. Okay? So I'm going to label this real quick. And there's a whole procedure for labeling this. Okay? So how I write this equation is I say, I subscript it with, we're doing a force diagram on our Q1 is being acted upon by Q2 by a distance r apart. So I subscript this is what is acting on our Q1 charge, and it's a distance r away. And that r is going to be squared. And we are going to be putting distances, not displacement here. So it's not going to have a positive or a negative r. It's just a distance, okay, a straight line distance. So we are doing our force diagram on our Q1. So this is what you're doing a force diagram on. So if I was going to do a force diagram real quick, I would write our Q1 right in the center of it. And even though it's only one dimension, I would still put our coordinate system on it. Label the coordinate system positive y, positive x, negative y, and negative x. So we're doing our force diagram on it. Okay, so we're doing that there. Now, what we would also do is say, suppose it's being pulled to the right by a charge Q2, and let's say that charge Q2 is a distance 0.1 meters away, and our distances will be in meters, not centimeters. Okay, so notice that this vector is pointed to the right, so it's going to be positive. So we would then put the positive in front. All right, and what we would also do is we'd put our r squared, put brackets first, 0.1 meters, and then we're going to square it. Again, this 2 is a subscript, so I'm going to make it look more like a subscript. So that'll be like 1.6 times 10 to the negative 19 coulombs. And we're doing a force diagram on our Q1, which would be like maybe 2 times 10 to the negative 12th coulombs, right? K is always 9 times 10 to the 9th. Newton meter squared per coulomb squared. So this is how we are going to write our charge equations. Okay, this is the format. Okay. Okay, so this would be our sum of forces in the x direction. So I'm going to move this off to the side. Oops. Get rid of this guy. And so once we have our force equation written, then we will sum the forces. In this case, we would only sum the forces in the x direction. Oops. Move this over too. And we would write our positive F Q2, comma 0.1 meters away. And it's pointing to the right, and it's a little vector. And then we would set this equal to the mass of this object, whatever its mass is, times its acceleration in the x direction. All right. And let's say it's accelerating to the right, so it's got a positive acceleration, and its velocity vector, it's not moving at that moment. All right? So the next line that we're going to do is we're going to go ahead and go, it's got a force to the right. Then we're going to put our Q1 at the center here. That goes first. And then we have the electric field due to Q2. And that charge is a distance 0.1 meters away. And we got to remember we have to square it. And that's going to be equal to the mass of charge 1 times its acceleration. Okay? So this is a little mini force diagram. Okay? And so this is how we are going to begin. Okay, the electric force, the Coulomb force. And that force is the attraction or repulsion of two or more charges interacting with each other. Basically, it's the electric field of one object acting on another. And in the next chapter, we'll get into electric field stuff. Anyways, so now that you understand this, and thinking of this equation right here, let's do some conceptual questions to see if you could put together the relationship between these objects. Okay? So, conceptual question number 1. Two positively charged particles, you have a positive 1q and a positive 1q. They're a distance 4d apart. And they're going to be repelling each other. And we're going to measure that repulsion as F1. Okay, so whatever that force is F1. Now, what we're going to do is let's think about their mutual repulsion now. If we make this positive 1q a positive 3q, and they're still 4d apart. So, if we increase the amount of charge on the other object, what will be the repulsion force on our positive 1q? Will it be greater than, will F2 be greater than F1? Will it be equal to F1, or will it be less than F1? So think about it, and think about the equation that we're working with, and go ahead and try this problem now. Pause the video. All right. So let's write a basic equation right up here. So let's call this F1, and we're going to just do a mini force diagram on this guy. So this positive 1q is going to be getting pushed to the right, and that is our F1 force. It's also going to be pushing this other force in the opposite direction. Okay, but right now we're just doing a force diagram on our positive 1q here. So that's going to be pushed to the left, but that's okay, we don't care about it. Now the charge is positive, so we're going to put our positive 1q right here. The reason why it's in brackets is because we don't want the charge being positive or negative to determine our force vector. We want the circumstances to determine the direction of our force. Now we're going to multiply that by the electric field of the other charge, which is this positive 1q. So I'll make this guy blue. Okay, which is going to be K times positive 1q, and it's over a distance 4d, and we're going to square it. So we're going to make a little equation here. Multiplying this all out, what we're going to get is kq squared over 16d squared. So we're going to get kq squared over 16d squared. All right. Now, I suppose you could write that a little bit differently. We'll call this, it's like saying negative 1/16 kq squared over d squared, right? So that's about that's like 1/16. Now, let's look at force 2. So this positive 1q is also going to be getting pushed to the left. So it's going to be negative F2. And it's pushed to the left. Our positive 1q is right here. Now, This charge is a positive 3q. So this is going to be k times 3q, positive 3q, all over 4d that we're going to square. Multiplying this out, the negative comes first. So this is going to be k times positive 1q times positive 3q. So that's going to be 3kq squared. Again, the positives don't matter. They're inside absolute value. And this is going to be over 4d squared, which is going to be 16d squared. Okay. So basically what we have is we have 1 over 16 kq over d squared compared to negative 3 over 16 kq squared over d squared. The negatives don't matter. That's just the direction of the force vector. So which number is bigger, 1/16 or 3/16? 3/16. So F2 is bigger than F1. All right. Hope you learned that. So we're going to be practicing building those equations, but also our little force diagrams. All right. Moving right on. Concept question number 2. So again, I'm trying to get you to interact with that Coulomb's force equation. So in this case, same situation, F1. You have two charges separated by a distance 4d. And so this positive charge is going to be getting pushed to the right with a force to the left with a force F1. Now, the two charges in the second part are the same charge, but the distance is decreased. Which repulsive force is greater? The force in the second part or the force in the first part? Okay, so try this out and pause the video now. All right. Well, nothing has changed from the very first instance where we have figured out that the force is going to be negative 1/16 kq squared over d squared. So that's the same as in the other problem that we did. All right. But now in the second part, this is also being pushed to the left. Let's do the force equation for this. So this is going to be F2 is getting pushed to the left. We're doing a force diagram on that positive 1q on the left. This positive 1q's electric field is pushing it to the left. And it's a distance d apart. So that's 1d that we're squaring. I recommend putting the brackets around that distance because we might just, as in this other part right here, we have a habit of just going 4d squared, right? Which that is not the same thing as brackets 4d squared. This is 4 times d, but this first one is 4d times 4d. All right, so it's pretty easy to mess this up. So do it like this, and even if it's d, put a 1d in front, and just do it for now. You'll be better off. Okay, so now this equation is going to be 1q times k times positive 1q, so that's going to be kq squared over, and 1d squared is just d squared. So that's like having a negative 1 in front. So which number is bigger? Negative 1 over 16 kq squared over d squared, or negative 1 kq squared over d squared? Again, the negatives don't matter. That's just the direction. So again, F2 is greater than F1. Okay? So getting you to work with that equation. All right? Let's try another one. Okay, so compare the forces due to the differently charged objects. So how would the force due to the positive 3q charge compare to the force acting on the positive 1q charge? So compare forces here. The force on the positive 1q charge, is that greater than, less than, or equal to the force that's acting on the positive 3q charge? So which force is greater? Positive 3q acting on positive 1q, or positive 1q acting on positive 3q? So pause the video now and try to answer the question. Okay, so we know from our very first exam concept question that this was basically F2, which we had worked out that that was F2, which is negative 3 over 16 kq squared over d squared. Now, let's look at this guy. This positive charge is being pushed to the right due to this other positive charge. So I'm just going to call this a force F, and its direction is to the right. So F, when we sum the forces in the x direction, is going to be equal to, it's pointed to the right, and we're doing a force diagram on our positive 3q charge, but it's being acted upon by this positive 1q charge. So that's going to be k times positive 1q all over a distance 4d that we're squaring. So solving this, we have a positive out in front. This is going to be k times positive 3q times positive 1q. That's going to be positive 3kq squared all over 4d squared, which is 16d squared. Pulling the numbers out from the letters, what you find out is this charge is pointed to the left, and it's 3/16 kq squared over d squared. And this force to the right is positive 3/16 kq squared over d squared. So they are equal in magnitude. So they are equal to each other. Forces are equal and opposite, and this is Newton's third law. Okay? All right. This is an offshoot of the last question. How are these force diagrams written? So we have a positive 3q on the number 1 spheres in each case, and we have a positive 9 built up on the positive 2 spheres in this case, on each of these spheres. Which one of these force diagrams is correctly drawn? Is it 1, 2, 3, 4, or 5? Pause the video now and try answering the question. Okay, well, what we had just learned in the last example is that forces are always equal and opposite, and the size of the vector is the proportion of this. So the size of this vector is 3/16, and it's the same size as this other poorly drawn vector, which is also 3/16 kq squared over d squared. So since both of these charges are repelling each other, the answer could be either 5, 3, or 2. But since forces have to be equal and opposite, the correct answer is 5. Okay? All right. Now, these problems are really cool. I like them a lot. And it's about if you could do these next couple problems, you truly do understand force, the Coulomb force equation. Now, suppose you had a positive 1c charge and a positive 1c charge anchored in place on this number line. Okay, so they're anchored in place and they cannot move. Now you're going to put another positive charge somewhere on this number line, and either positive or negative, it doesn't really matter, but in this case let's put a positive 1 Coulomb charge on this number line such that it can move. But you need to put it in a place where it won't move. Where will you put it closest to? 1, 2, 3, 4, or 5. So where will you put this third positive 1 Coulomb charge that is free to move on this number line, but it won't be able to move because the other 2 charges are acting on it? Go ahead and try this out. Pause the video now. Okay, if you put the positive 1 charge here, so let's say I put, I'm going to just put it right here. Say I put a positive 1Q charge right here. Okay, well, I'm going to highlight this as the black charge, and this will just be, I'm going to actually make this one red, and we're going to be working with a purple charge that we put right here. Nope, purple. So we're putting a purple 1Q charge right here. Well, this positive 1Q charge is really close to this black positive 1 Coulomb charge. So that force is going to be really large, and it's going to be to the left. So this is due to the black positive 1 Coulomb charge. That is like a distance d away. Okay? But this red positive charge, and let's just say this distance is a distance d away from here. Okay? This black positive 1 Coulomb charge, the red positive 1 Coulomb charge is acting on our purple charge, and it's also going to be pushing it to the left. But this guy is a distance 1, 2, 3, 4, 5. So it's a distance 5d away. So that means it's going to be 25 times, because you got to square that, smaller than the other charge. Okay? So you put this purple positive 1Q charge right here, it's just going to take off to the left. And conversely, if you put it right here, well, the black positive 1 Coulomb charge is going to shoot it to the right, and this, actually, it should be much smaller. The black positive charge is now 5d away from it, and the red charge is now really close to it. So you're going to have it shoot off to the right. The only place you could place this positive 1Q charge is right here in the center. If you do that, the red charge is going to push it to the left. And it's a distance 2d away. And the black charge is going to push it to the right. The same amount, because it's the same distance and it's the same magnitude charge. And there you go. So you'll want to put it right here at 3. So 3 is the correct answer for this concept question. All right, let's try another one. Where will you put a positive charge that is free to move on this particular case? So again, the negative 1 Coulomb charge and the negative 2 Coulomb charge are anchored in place and cannot move. You're going to place a positive 1 Coulomb charge that is free to move somewhere on this number line closest to it, and you want it to not move. Meaning, just like in this other case, you want the sum of forces to sum to 0. Okay? So where will you place it? Closest to 1, 2, 3, 4, or 5. All right, pause the video now and try this out. Okay, so starting with the same format that we just did, so I'm going to put a red positive Q charge right here. And if we do that, I'm going to call this purple, and I'm going to call this guy blue. This blue charge is going to pull it to the right, and it's going to be a huge amount. So I'm actually going to put it down here. I'm just going to adjust the vertical part here. So this positive 1Q charge is going to get pulled to the right a huge amount, which is similar to this. So it's going to be a positive, and it's due to the -1 Coulomb charge of the distance d away. This -2 Coulomb charge is at a distance 5d away. So its force is going to be also positive, and it's a -2 Coulomb charge, and it's distance 5d away. So this is going to be 25 times smaller than this. But again, if you put it right here, it's just going to take off to the right. And the other case, if you put it over here, it's going to get pulled to the left. Now, if you put that charge right here in the center, and I'll move this down here as well, this positive 1 Coulomb charge, it's going to get pulled to the right with a greater force than it'll get pulled to the left. So it's -2 Coulomb, it's a distance d away. When it's getting pulled to the left, it's only going to get pulled to the left with half the amount that is being pulled to the right. So overall, it'll get pushed to the left. It'll get pulled to the right. Okay? So what we should do is we should actually place it. Actually, if we put the positive 1Q here, closer to here, this -2 Coulomb charge is actually only going to get stronger, while this -1 Coulomb charge pull is only going to get weaker. So our best option for putting the positive 1Q charge is right here. Somewhere in between 2 and 3, but closer to 2. The -1 Coulomb charge, the force to the left, is going to be equal to the force to the right. Distance d away. And this is approximate, you know. I'm using symbols here. This is 1, 2, 3. So 3d is away. Okay. And again, what's happening? I'm going to take this guy in a second and explain a little bit more. So we're going to want to place it closest to 2. So the correct option is number 2. But here's what I mean. What we're doing is little force diagrams. When we sum up these forces, this guy, for example, we would have a negative, and we're going to put our red positive Q, our positive 1Q, and the -1 Coulomb charge, at electric field is acting on our red positive Q, and it's a distance d away, right? Now we're going to add to that the positive guy, because its vector is pointed to the right. It's also acting on our positive 1Q charge, and the purple -2Q, 2 Coulomb charge, is a distance 3d away. When we square that, this is going to act on the mass of the red Coulomb charge, and hopefully when you add up these two things, it gets close to zero, such that this acceleration is zero. So when these two forces are equal and opposite, okay, well, are equal in magnitude but opposite in directions, that is zero, and zero divided by the mass of this guy is just going to be equal to the acceleration, which hopefully will work out to be zero. So that's the reason why it does not move. Okay, so that's what we're talking about here. Okay, let's do one more. So we'll do our last conceptual one in this, and we'll move on to two smaller little parts and then do some calculations. So we'll quantify some of these things. Okay, so in this problem right here, we have it's the same problem. We're going to again put another positive 1q somewhere on this number line such that it will not move. Now here we have a blue -2 Coulomb charge, and we have a red positive 1 Coulomb charge. So where are we going to put our black positive 1 Coulomb charge on this number line such that it will not move? Meaning the forces will be in balance and nil each other out so that the acceleration is zero. The starting acceleration is zero. All right, so try this out. Pause the video now. All right, so let's start over here. I'm going to change it up a little bit. I'm going to put the positive 1 Coulomb charge right here. If we do that, we're really close to this -2 Coulomb charge. So it's going to pull it to the left, 2 Coulomb, and it's a distance d away. Now this red positive 1 Coulomb charge is going to be repelling it, but it's so far away that it's going to be such a small value. It's not only small in charge, but it's going to be, well, 1, 2, 3, 4, 5 Ds away. Okay, so when you do this, these forces are not equal in size. It's going to definitely begin accelerating to the left. Let's try putting it in the center. Okay, so if we put it in the center, 1 Coulomb, the positive 1 Coulomb charge, the -2 Coulomb charge is going to pull it to the right, and that'll be like this, -2 coulombs, comma 2d, right? But this positive 1 Coulomb charge is still half as strong as the -2 Coulomb charge because it's smaller in magnitude. So it's got a positive 1 Coulomb charge, and it's a distance 2d away. So even though they're the same distance, just like in our very first concept question, they're small. The vectors are smaller in size. So it will then begin to accelerate to the right, okay? Because you have positive 2 to the right, -1 to the left. It'll begin accelerating to the right. Our only option, and also, by the way, anywhere you put this in here, it will begin accelerating to the right. Our only option is putting it right here, closest to 1. Okay. Now that positive 1 Coulomb charge is going to be close enough to push it to the left, but far enough away from the -2 Coulomb charge for it to not affect it as much. So somewhere over here, I think it's actually further out here, but it's definitely on this number line closest to the positive 1, to this number 1 position. So the correct answer we're looking for here is this one. Again, since these two forces would be about the same size in same magnitude but opposite directions, when you sum the forces, that'll be 0. So divide that by the mass of this positive 1 Coulomb charge, 1 Q charge, and that would also be 0. Okay? All right. Let's talk about these the concept questions here. Now, even though these charges are forcing each other, they're pushing on each other, they also do have a velocity and acceleration. Okay, so let's talk about this. So suppose you held a positive 1q and negative 3q really far apart, and then you let them go. And when they finally got to a distance 4d apart, they had so this guy has a velocity at this point of 1v to the right. So at this point, this positive 1 Coulomb, this positive 1q charge has a force, a velocity to the right of 1 velocity, or like 1 meter per second, and it's also got an acceleration to the right of positive 1 acceleration. Okay? Now, suppose you let them continue moving, and now they're at this point. Okay? Compare the velocities to each other when they're here versus here, and compare the acceleration to each other's in the first case to the second case. And then finally, in the last question, when you let these two go and they got 4d apart, and then they started moving to 1d apart, during that motion, were they speeding up, slowing down, or constant velocity? All right, so try to answer these questions. All right, pause the video now. Well, these two objects would be have an equal and opposite force on each other. They would be attracting each other with the same force, but this object and they would also be accelerating and moving towards each other. And whenever you have a velocity vector and acceleration pointed in the same direction, you are speeding up. And by the time they get close enough here, this positive 1q charge its velocity vector would have gotten way bigger. And since the force is greater here, this force is, again, it's going to be 3/16 kq squared over d squared, and this force is just 3 kq squared over d squared, right? So since its force is increasing, that means the acceleration is also increasing. So not only is it speeding up, which means the velocity vector is getting longer, the acceleration vector is also getting longer because the force of attraction is getting larger. So basically, this is going to be increasing. The acceleration is going to be increasing because the force is increasing, and they are going to be speeding up. And that's what the motion looks like with two attractive objects. When you let them go, their velocity is going to be increasing, and since they're coming together, their mutual attractive force will be increasing, which then means the actual acceleration vector would be increasing. So that means they're going to be speeding up. Okay. Now, let's do the opposite. Suppose you had a positive 1q charge and a positive 3q charge, a distance d away, and then you release them. So let's try this guy. Let's do the force on this guy. Let's say it has an initial velocity of, not doing a force diagram, let's say you released it and let it move a little bit and had an initial velocity of positive 1v and had initial acceleration of positive 1a. And that is with this mutual force of 3 kq squared over d squared. Now, what will be the velocity and acceleration on the positive 3q? Okay, so what is going to happen to the velocity as it moves from d to 3d as they repel each other, to 4d away as they repel each other? What's going to happen to the velocity? What's going to happen to the acceleration vector? And how would you describe its motion from the first to the second? Will it have been speeding up, slowing down, or constant velocity? Try this out and pause the video now. Well, over here, the force vector is going to be huge. It would be 3kq squared over d squared, and this would also be 3kq squared over d squared. But when it gets further out, now it's going to be positive 3/16 kq squared over d squared. Okay, so to explain what's going on, okay, got to be careful about this. So this is going to be 3kq squared over d squared, and I'm summing the forces in the x direction over here. That's going to be equal to the mass times the acceleration. And so the acceleration here is going to be 3kq squared over md squared. Over here, this will be 3kq squared over over 16d squared, which is equal to mass times acceleration. So its acceleration is going to be 3kq squared over 16d squared. So this acceleration vector is going to be smaller in size. So the acceleration vector is going to decrease in size. But that doesn't matter. See, right at this instance, it's going to have 1/16 of the velocity, but it's been accelerating the entire time. So if you have an acceleration or a force on you pushing you, and even though that force is dropping off over time, your velocity vector would still be increasing the entire time. So even though it's, if this is, let's say this is the original size of your 1v, which this is the original size of the 1v, but out here, you're still adding one velocity to it. Even though your acceleration vector, let's say, is this big, and now it's, 1/16 the size, so this would be 1/16 a, you're still speeding up. You're still getting pushed. So the velocity on this would be decreasing in size. So I got to be careful about what I said. Your velocity vector would be still being added to the entire time. So it would be increasing in size during the entire motion from the beginning to the end. But the acceleration vector would be decreasing in size. It would still be pointed in the same direction. And no matter what, if your velocity vector and acceleration vector are pointing in the same direction, you're still speeding up. I know, that's a weird question. It's really weird. But just to summarize this, if I said you had two charged objects and you let them go, and all I said is during their entire motion, they were speeding up, okay? And let's say they were a distance apart and you let them go. During their entire motion, they were speeding up. Well, and I said, are they opposite in charge or the same in charge? You would have to say, I don't know. It could be either. But if I said this, I have two charged objects in space and I let them go, and their acceleration vectors started decreasing in size. Well, now you know they're repelling each other and that acceleration vector is dropping off in size. Okay? Where over here on this red case, this guy's acceleration vector is actually increasing in size. It's actually 3 times the size of the original one. Okay? So it's very interesting how this works. So no matter what, in both cases, they're speeding up. In fact, if you had 2 charged particles in outer space, they will always be speeding up if they're the only 2 things acting on each other. Okay, they will always be speeding up. They will never be slowing down, and they will never be moving at a constant velocity. They will always be speeding up no matter what their charge, opposite or same sign charge. Okay, let's do one of the quantitative problems right here. Okay. And let's practice doing force diagrams. So, this quantitative question number 1 is the same question as this conceptual question number 7. All right. We're just going to be using, we're actually going to be using numbers. Now, you have a -1 Coulomb charge and a -2 Coulomb charge. They're separated by half a meter. And they're asking, where will you put a +1 Coulomb charge somewhere on this number line such that it will not move? Okay? Now, what we had learned on conceptual question number 7 is if this is the midpoint, we want to actually put it right here. We want to put our +1 Coulomb charge right here. Okay. Okay. And that is because, and I'm going to draw a little force diagram. I'm going to do this from start to finish. This is similar to one of your homework problems. So this is going to be +x, +y, -x, and -y. I still do a 2-dimensional force diagram every time. Now, we put our +1 Coulomb charge right here in the center, and then we're going to do a little force diagram on it. We're going to be putting it in such a way the force to the right has got to be equal to the force to the left. Okay? So we want this guy, so I'm going to make one purple. So this is our purple -2 Coulomb charge. It's going to be pulling it to the right, the +1 Coulomb charge. So it's positive, and we got a -2 Coulomb charge, and it's some distance away. Not going to worry about that just yet. This is a blue -1 Coulomb charge. It's going to be pulling it to the left, and it's got to pull it with the same amount of force, just in the opposite direction. Remember, we're placing it on this number line so that these two forces are equal. That way, when we let it go, there will be no acceleration on this object. Okay? Now, here's the problem. We don't know the actual distance. We know these two things are separated by half a meter. Okay, so we have to make up some stuff here. Let's do this. Let's say it's a distance x from the -1 Coulomb charge. So I am going to put that distance right here. All right. Now, if that's a distance x and the whole thing, the two main charges are separated by a distance half a meter, what is this distance apart between these two things? So what is this distance from here to here? Well, for us to figure out this distance, what basically is, they're separated by a distance of 0.5 meters, okay? But you're taking out this distance x from it. So in other words, this distance is 0.5 meters minus x. That will be this distance from the +1 Coulomb to our -2 Coulomb charge. All right? So we'll call this the distance x, and this is the distance 0.5 meters minus x. All right, let's sum our equations in the x direction. Again, we are practicing our force diagrams that you learned in Physics 111. So this is a force diagram. Now, it's not going to be moving or accelerating when we first put this charge down. So hopefully it'll stay that way, which we're assuming it will. All right. So starting with the equations, I always start from left to right. You don't have to, but I do it. We have our negative F of our force caused by the negative 1 Coulomb charge on our positive 1 Coulomb charge. That is distance x away. We're going to add to that the negative 2 Coulomb charge acting on our positive 1 Coulomb charge. That is a distance 0.5 meters minus x away. And set this equal to mass times acceleration in the x direction. The reason why I write it this way is this, the subvariables here tell you what to write for the electric field. And as long as you know you're acting on your positive 1 Coulomb charge, all of the information that you need to construct the Coulomb equation is right here. Okay? Now, we're setting this equal to mass times acceleration. This acceleration is 0. Therefore, any mass times 0 is going to be 0. Now let's construct our Coulomb equation. So this can be the negative that comes down first. We're doing a force diagram on our positive 1 Coulomb charge. The electric field due to the negative 1 Coulomb charge is right here. It's all right there over a distance x squared. Now the purple negative 2 Coulomb charge is acting on our positive 1 Coulomb charge. And all of its important information is right there. It's K times a negative 2 coulombs all over 0.5 meters minus x that we're going to square. And that's, again, that is just a distance. It's equal to 0. Now what we're gonna do is we're gonna multiply all this out. So we're gonna have a negative positive 1 Coulomb times K times negative 1 Coulomb is just gonna be K times 1 Coulomb squared. There is no sign in the front because the absolute values take it off, over x squared, plus positive 1 Coulomb times K times a negative 2 coulombs. That's going to be K times 2 coulombs squared all over 0.5 meters minus x that we're squaring, which is equal to 0. Now what we're going to do is add this to both sides. Add the K times 1 Coulomb squared over x squared to both sides. So I'm going to do this. Just going to grab this, duplicate it, have a equal sign, drop it right there. Duplicate that, and that's what we get. Now what we're going to do is start reducing this equation. Okay, so I'm going to multiply both sides by 1 over K, and when we do that, those K's will cancel out. And then I'm going to multiply both sides by 1 over C squared. So the C squares will cancel out. I'm trying to get this thing to become more user-friendly. Now what I'm going to do is multiply both sides by x squared. And both sides by 0.5 meters minus x squared. And when we do that, we get something that looks like this. X squared times 2 equals 0.5 meters minus x that we're squaring. Now we're tempted to FOIL this out and then bring this onto the other side, and then you get a quadratic, which you can totally do. It's just easier to just square root both sides. It's a little trick I learned when doing problems like this. Okay, and when we do that, what we get is x square root of 2, and we get 0.5 meters minus x. Okay, now what we're going to do is add x to both sides. And when we do that, we could factor out this square root of 2 plus 1 equals 0.5 meters. Square root of 2 is 1.414, so this will be x times 2.414 equals 0.5 meters. So x is going to be equal to 0.5 meters divided by 2.414. And when we figure this out, let's figure out what this equation is going to be. That's going to be 0.5 divided, so 0.5 divided by 2.414. 0.207. So I'll just keep it in that way. So 0.207 meters. And that is x. So that is the distance, how far away in the middle that we put this such that it will not move. Okay? Well, that is going to be all for today. This is a lead-in to our 1.1 tutorial where we're going to practice constructing equations, the Coulomb equations in one dimension with just 2 objects and also 3 objects. Okay? So we've already done quite a bit of this. Again, if you haven't watched the video on 1D vector addition, please do so. It really does help out. Okay? I hope this helps you. Have a great day.